So this talk is about Lisp. Oh, there's a big echo. Okay, so it's about Lisp and its applications in SDN and NFV. So I'm going to give a quick overview of Lisp and then how it plays in the context of SDN. And then we're going to look at some of the open source options that are available now for Lisp. And then we'll go into more detail on how Lisp is implemented in OpenDaylight and what you can do with it. We'll have a couple of demos also that I'm hoping that I can show you live. We'll see how that goes because I have to connect via VPN, and it looks like for some reason the Wi-Fi here doesn't work well with that. And then I'm going to pass to Sharon from ConteXtream here to talk about the NFV side of things and how Lisp plays there. So just by a show of hands, how many people here are familiar with the Lisp protocol? OK, a fair amount. Perfect. So I'll be quick on this. So as it's clear from the name, Locator ID Separation Protocol, Lisp protocol tries to provide a separation between host identity and host location. And it does that by creating two different namespaces. The host identity or endpoint identity namespace, which represents the identity of the hosts, and the routing locator or RLOC namespace, which represents the address by which you can reach the host, or basically what you can route your packets based on. And then it provides a distributed mapping system where you can create a mapping between these two namespaces. So you would say this host with this EID is located at that RLOC. And then Lisp routers can go look that up and then encapsulate packets there. So basically, to get a little more detail, there are two planes. There's a data plane where it's basically simple encapsulation and multi-tenant overlay encapsulation. It can do MAC and IP and IP and IP. It's very similar to VXLAN in terms of format of the encapsulation headers, except for Lisp was initially designed to do IP and IP. And so that's the data plane. And then there's a control plane, which provides this mapping of this overlay address space to the underlying physical network. And it also supports introducing policy into that mapping. So you can basically define the mapping of the host identity to the host location. And you can introduce some additional policy on how to reach that host. Examples of policy that you can include are multi-homing and load balancing, that sort of thing for one case. For instance, you can have your host identity mapped to multiple locations. So you'll have multiple RLOCs for it. And then you can have priorities and weights to enforce how you want that host to be reached. So you can give priority to one location over the other, or you can basically split weight and split the traffic or the load over the two locations using them both. Another example is traffic engineering and service chaining. So that's another kind of policy that you can insert, saying that in order to reach that host or that endpoint, I don't want to give you the direct location, but I'm going to give a path. And a path is a set of hops, a sequence of hops that you need to go through to reach that endpoint. And at every hop, assuming that the hops, we're assuming the hops are all Lisp enabled basically, and every hop will get the encapsulated packet, decapsulate it, look at the inside the endpoint destination, the EID, and see, and again, if it doesn't already have it locally, it will fetch from the mapping system the policy to reach that EID. And based on that, it will re-encapsulate and send to the next hop. And so it will be done this way, hop by hop, until it reaches the destination. And one other thing is that when Lisp gets the the mappings from the database. If it doesn't have it already the first time, it will do a lookup, but it will cache it locally. And so for the rest of the packets in that flow, the mapping is already cached locally, and there won't be a lookup. So that's another policy that we can do with Lisp. So now going back to SDN. Well, there's a hard to define concept, I suppose, or different properties to agree on. But there's a few specific properties that I think everyone in the SDN community agrees on, and that is decoupling of network control from the network data plane, and programmability of the network, and also openness. So these are the three properties that I think the SDN community agrees on that would define, or at least be the common denominator for an SDN supported network. And these are all properties to reach the goal of increasing flexibility and development speed for adding features and functionalities into the network. Now, as we just took a look at the overview of Lisp, it has a separation between a control plane and a data plane. And it it has a encapsulation-based, multi-tenant encapsulation-based data plane, which can provide network virtualization with supportive multi-tenancy in a dynamic way, meaning that you don't need to set up the entire overlay beforehand. As long as you have a Lisp network in place or Lisp-enabled nodes in place, the overlay will be set up dynamically by looking up the mapping system as the packets arrive. And of course, it's open. It's in the RFC in the IETF. And one last thing is that you could define basically programmability to the mapping system. And as we saw, you could define policies and forwarding policies in the mapping system. And then that provides some programmability that then you can use to enforce those policies in the data plane. So that's kind of a summary of why we see Lisp as a good fit in this context. Now looking at the options that are available in the open source community for Lisp. So the main one is lispmob.org. And it provides a Lisp router code for Linux, Android, and OpenWRT. So you can go to lispmob.org, download the code, and run it on your Linux, and you have a Lisp tunnel router. You won't have a mapping system. It will be just a Lisp data plane and control plane on the that runs on basically a Lisp router. Then we have Lisp data plane enabled in OpenVSwitch. So you can set up a Lisp vport in OVS and have a Lisp overlay. And we have the Lisp control plane, or basically the mapping system side of Lisp, which provides the EID to our log mappings in the OpenDaylight, which is what I'm going to go into more detail right now. We also have integration with OpenStack coming soon. So hopefully very soon you can go to OpenStack and using the OpenDaylight Neutron plugin, set up your Lisp network and introduce all kinds of cool policies. Okay, so let's take a look at the OpenDaylight Lisp implementation. This here puts Lisp components into context with respect to the rest of modules in OpenDaylight. As you can see, there's the Lisp service in between. That's the main module that provides the mapping system services. There's the OpenDaylight API. So there are REST APIs on the northbound that provide programmability to the mappings to the Lisp service. And then there's a Lisp plugin on the southbound where Lisp-enabled devices on the data plane can use to query lookup mappings and register mappings in the Lisp service in OpenDaylight. Also, as we said, we have OpenVSwitch where Lisp data plane is enabled. There we don't have Lisp control plane, so what we can use is we can use OpenFlow and OVSDB plugins to basically emulate what the Lisp control plane on the data plane device does, to look up the mappings and then install the right flows so that we can have a Lisp overlay across Lisp-enabled devices that include examples like Lisp Mop, hardware Lisp devices, or Open vSwitch. So this is an example. For instance, you can set up load balancing or traffic engineering policies using the northbound API. The REST API is used to set these policies in the Lisp service. And then you can use the Lisp plugin to look up these policies from the mapping system and then create this Lisp tunnel or Lisp overlay across different kind of data plane devices that you have. And as we said, for OVS, we have to use OVSDB and OpenFlow to kind of emulate that control plane. So now let's go into more detail of what the Lisp service actually inside OpenDaylight has. So this is a quick overview of the components there. There's a northbound, southbound plugin and a Java API. And then inside the implementation, there is a map server interface, which supports the interface to installing mappings in the database, and the map resolver, which supports the interface to actually looking up or querying the database. And the DAO is providing an indirection layer to access the actual database where all the mappings are stored. Now, going through the northbound API, we have two main resources basically that we can play with. There's the main thing is the mapping, of course. So you can insert mappings or install mappings that provide location plus policy information for one EID, which would be like when you want to reach that EID, you have to follow those policies and reach that RLOC. Or you can put in a policy and a mapping for a combination of a source and a destination. And that's kind of going towards the direction of basically putting a policy in or a location in for a flow, not just the destination. Now here, it's not a full flow. It's really like a two-tuple flow. But that's the direction that it's going. And it's mostly useful in this context where, for instance, you want to say, I have a prefix of this address space, which is my marketing department, and I have a prefix Y that is my engineering department, and I want to insert a policy saying that if any packets are going from the marketing to the engineering, I want this, let's say, service chaining pass, or I want this firewall to be installed. So that's how you could use that part. But before inserting any mappings in the database, you have to first define a key for that mapping. And so that's why that's what the key is used for. And now different kinds of basically mapping address types are supported in, yes?
Quick question for you. For the source desk paths, you said you support prefixes. How do you guys deal with the differences in longer prefix on the source or shorter prefix or longer prefix? What's the policy that you know which way you're going to map, which entry is really going to map if you've got more than one length of prefix in your entries?
Right. So in Hydrogen, that's very limited right now. So I can say that that's not fully spanned out yet. But we're hoping to do a better job at it in the next release. On the other hand, one thing about this mapping service in the ODL, which is different, is that it's not using the usual hierarchical mapping with hierarchical addresses that is defined typically in Lisp RFCs. So it's actually using a flat mapping system. It's using a flat, right? So, yeah, exactly. So that's how we're doing flat. And the way we support prefixes is kind of emulating it to a flat database. So, but again, there are of course performance issues. So we're working on that to do a better job. But anyway, you can kind of at least try it out now. Okay, so going back to the address types. We have IPv4, IPv6, and MAC addresses supported. We have distinguished name, IS numbers, segment ID, which is the multi-tenancy kind of, or tunnel key equivalent, the sources as we discussed, and then the explicit locator path or this traffic engineering policy. So this is an example of installing a key. You have the URL to install a key, and that's, you give the content via a simple JSON file. So here we're saying that the key is ASDF, and the EID that we were registering this key for is 10.0.0.1, and there's a mask length associated with it. So it's a prefix of larger than /32. Same for mapping. We use the JSON file to install different mappings. So this is an example here where you can say you first have to define the key that was defined for that prefix, and then you say install the mapping for it, which is the locator part on the bottom, and you're giving an IP address and a priority and a wait in this case. So there's no policy, there's not much of a policy here because it's only one locator. But this location part, locators part can be extended, and it can include multiple hops and modify the play around with priority and wait to do all sorts of load split and so on. So now I'm going to attempt to do the demo. As I said, the only problem is that we have a little bit of issue with the Wi-Fi here and the VPN that I need to connect to. So we'll see how that goes. Otherwise, I can show just some of the examples. Okay, there we go. So actually, let me go through the slides back real quick. Well, let me run the controller. Okay, so while that is running, I'll go over what we do in the demo. So first of all, big thanks to Laurie Jacob. He helped a lot with setting up this demo, and also, of course, thanks to Alberto and the entire ConteXtream team that worked on this. So here's a demo topology. We have 3 LISP mob nodes. There's a client and 2 servers. And we have the OpenDaylight running on a separate machine. So what I'm going to do first is I'm going to define the keys and mappings via the REST API into the ODL LISP project. And then I'm going to go ahead and ping one of those servers. So basically, the servers are both kind of multi-homed EID. So the EID 2.2.2 is mapped to both of those servers. And my client is 1.1.1.1. And so when I ping the server address on the server identity, basically on the client is going to go to the mapping system or to the OpenDaylight via the southbound plugin. It's going to look up the mapping, and it's going to get the address of the first server. And so the ping is going to start going back and forth. Then I'm going to go to the northbound API again and change the policy. And I'm going to say now I'm going to give priority to server 2 for this EID. So then you'll see that the ping will kind of transfer from the server 1 to server 2. Then I'm going to attempt a service chaining policy. So what I'm going to do is go to the northbound API and this time insert a service and say to reach the 2.2.2.2, I want you to go first as a first hop to the service node, which is another LISP mob service node, and then I want you to go to the server. Still going to service 2, of course. And so then the client is going to receive that policy change, and it's going to send the traffic to my service node, and then the service node is going to forward that traffic to the endpoint, the server. Now, my service node is a very, very basic firewall. It's just using IP tables to allow or drop the traffic for this ping. So then I can go basically to my service node and say, change the policy to dropping that traffic. You can see that the ping stops, and then I'll restart that again, and the ping goes on. So basically here we're kind of inserting a service and then modifying the service policy and seeing that that is in fact on the path of our server. So. Okay, so yeah, actually I didn't quite fully hear that too. So.
When the traffic is directed towards the service node for services, is the root program on the service node directly, or the service node has to go up the mountain to what has to be done?
Okay, so the service node in general. This version of this version of Lisp in the Hydrogen release does not support a proactive mapping system. So everything that we described here, and that was just my last slide. So everything is kind of pulled from the mapping right now. So the client pulls the change of policy, and so does the service. The first thing on our agenda for the next release is to enabling a push as well when the policy changes. And that's, the mechanism exists in Lisp, it's just that we didn't get enough time to actually implement it. So right now it's a pull, but hopefully in the next release, or even maybe if we have like mini releases, we'll have that coming.
The policy change you're making here, are you using also OpenDaylight, or you have to do it directly? You have
the policy change on the services directly.
Why don't you use OpenDaylight to do that? Support policy too?
So the change that I'm making on the service is a firewall policy. So assume that here we have a little, look at this service as a Lisp router in front of any kind of service that you can have. Like, you can put a firewall, ASA, Cisco, whatever in there, or a load balancer or whatever. So that's a service, and the policies for it can be installed directly to the service. We could come up with scenarios where potentially we use like applications on top of OpenDaylight to also use those, but that's it's more generic than just Lisp. You can put any kind of policy there. And now, in the demo, it's just I'm just using like a Linux IP tables as a firewall service. But it could be even a hardware device or so.
When you have a successful ping, the return path going to go back through the service node, or is the return path independent of the trigger?
Okay, so the return path is independent, but you can set the policy for the return path as well to go through the service node. Here, I'm not doing that. So the return path is going directly, not through the service node. Yes?
So in ODL, there is a topology module,
Right.
right? Topology module base level functions and the topology database as well.
Right.
So from what I understand, that's used to learn the locations where you're supposed to connect to the network.
Right.
So here, you're also kind of
Right, so this topology is not actually using the topology service in the controller. And the reason for it is that we're using LISP mob nodes here, and they don't, the LISP mob client basically which we get from the lispmob.org is not integrated necessarily with OpenDaylight as a whole. So what it does is it is configured with a mapping system. And here what we do is we point as the map server or as a mapping system, we point these LISP mob nodes to the OpenDaylight. So that's why they fetch the policies from there. So the LISP mob nodes are configured to kind of fetch those policies. Now, again, in the next release, hopefully we can actually get the LISP mob code also integrated with that. But for Hydrogen, we were just working on the control plane implementation inside the ODL. So that big box where you see. But if we actually use OVS, so Open vSwitch as a LISP node, then that will show up on that will register with the topology manager and it will show up. So, but then you can't use the LISP southbound plugin. You'll use the OVSDB and OpenFlow plugins to set flows up for that. So that is possible if you use OVS, but not right now with the LISP mob. Yes.
So, what is the facility of doing load balancing based on the load?
So you can insert multiple locators, and for every locator you can set up a priority and a wait. And priority says which server has priority, which RLOC has priority over the other. So the one with the lowest priority basically wins. So that's the only one you use. If the priority is all the same, then you specify a wait. And the wait is kind of used as a relative number. So if you have 3 locators and you have a wait 20, 20, 30, that's how your flows are going to be split across.
But how do you know what connections are still active? Because the return path is not through whatever the controlling path is. So you don't know what the load is on any, or how many connections are active on any server.
For the demo, you mean?
Or in general, how would you implement it?
Statistical balance, not one system.
Okay, that makes sense. Okay.
Right. Thank you.
So I have a question.
Yes, please.
I had a question. So in the ingress, on the ingress side, when the LISP client figures out what destination the RLOC is, right? So when the packet gets sent to the appropriate server, on the egress side, you can do learning like a regular layer to switch, right? Meaning, if for this particular the 1.1.1 IP address, you need to use the source IP of the output header.
Right. You could do learning, and that was kind of also considered in LISP, but here mostly because LISP was designed for not just a data center setting. It was designed for across the WAN, multiple organizations, blah blah blah. So because of security and stuff like that, we don't do kind of looking at that packet. But yes, it can be done.
On the same line of questions, how do you make sure that this LISP server is actually up? Is there a way that your mapping service actually pings the server or something? You made an entry. What if the machine goes down? How do you make sure that this service actually fails what the stores?
What if you mean the OpenDaylight goes down, or the
one of the servers goes down? How do you take it out of the map?
Oh, okay. So again, for the demo here, we're not doing that, but you could write an application on top. So there is a service where all of the LISP nodes basically periodically register. So there's like a keep alive kind of thing going on. And if the mapping system doesn't hear for a certain period of time from one of them, then it will mark that as down, and so it will automatically, the LISP mob will automatically use the other one if it's available.
So return path, the packets don't come to the service
In the demo directly, but you can configure that.
What if the service node actually transforms the packet?
Transforms the packet. It's so. Sorry?
It's a NAT service.
Well, we're assuming a service that does not modify the header right now. Well, obviously for this scenario, this is kind of two-side questions. We do support LISP traffic going through NAT, but inserting a NAT service intentionally is not yet supported like this. We're assuming like promiscuous mode services that don't modify the headers, the inner headers. Okay, so let me see if we can, okay, perfect. Okay, let me just check to see if we have everything working. And now I'll do, so I have these 3 machines here. Then I have a Postman client to do the REST APIs. So what I'm going to do is first start these LISP clients on the 2 servers. Should be. Oh, people are coming to the front. Well, yeah, there's not much that you need to actually see here. So I think we can kind of skip that. This is just, I'm just running the clients. Okay, so the more interesting part is happening here. So this is the Postman client. So what I'm going to do is add a key for this, the first client that we just talked about. And then I'm going to get the mapping for that. And let's take a look at. So here's the mapping that we get right now. So as you can see, this is a client. It's running on this IP address, and that's about it. This is the EID, and this is the IP address, and there's like the rest of the policy flags. Now I'm going to add the key for and introduce basically the servers in the mapping system. So I'll add the key, and then first I'm going to add the mapping, and the mapping has the 2 servers. One is at the .37, and the other one is at .44. But the priorities are different. So as you can see, the priority of this one is 126. This one is 127. So I'm going to send this mapping to the OpenDaylight controller. And the delay is not because the controller is slow. The delay is because I'm using a VPN. But it should come sometime soon. Okay, there we go. So now let's see if we actually got the right mapping. So now we have this mapping for 2.2.2 in the controller, And what we see is the two locator for it, the 37 and 44. So now we have the mappings for both in place. And now I'm going to start a ping. So going back to this is the second server, and this is the first server, and you can see that, I know the font is hard, but at least you can see that these the packets from 2.2.2 to 2 and 1.1 are being seen, and there the ping is going on. So now I'm going to go over to our REST client, and I'm going to change the mapping, and I'm going to change it to server 2. And how that is done is that pretty much it's the same mapping, but what I'm doing is that I'm reducing the priority. Here it is. So I'm reducing the priority for this .44 locator from whatever, it was 126 before, or 127 before, and now it's 125. So the prioriters work the other way. So the lower it is, the more likely that you have to pick it. So I'm going to reduce the priority for this one, saying that I want to give priority to this server. And now we go to the second server, and we see that now it all of a sudden starts receiving the pings. And if we go to the client, of course the ping is still going on. And if we take a look at here, it's now encapsulating to 44 here. And this is like a list of locators that it already has, together with the priorities that are registered here. Okay. So that's that. Now I'm going to try to insert my service node. So this is running LISP. And this is the ELP case. So I'm going to insert that one. And this is saying that I want to insert a mapping. And let's take a look at that. So here, I'm introducing a set of hops. And what I'm saying is that we have what we had before, but now we have a lower priority, which is 124, locator, which is composed of two hops. The first hop is my service node. That's the locator here. And the second hop is again one of the servers. And this first hop is my service node here. So now you can see that it's kind of getting the packets, and you can see here that now it has the 12.12 address, and it's encapsulating to that. And going to the ping again, that's of course still running. Okay. So now what I can do is actually go to my, this is that .12 service node, and here I'm going to do a, right now, as I said, I'm using IP tablets to kind of emulate a firewall. So now what I'm going to do is I'm going to drop any traffic that goes to 2.2.2. And obviously the ping stops, and I load that policy again, and we see that the ping starts going on again. So that's kind of showing how we insert this service, and then we can modify the policies on the service to to basically modify the traffic path. OK, so now I'm done with this part. The tutorial that we just, kind of the demo that we kind of went through, at least the first part of it, not the service training, but the first part is described over the wiki. And so if you would like, you can go on and take a look and try it out. As I said, the first coming up is this proactive pushing that is not supported in this case. And then also we have support for OVS. Lori has worked very hard on that. But so we could actually show a scenario where one of these servers was an OVS node. And we would set it up via the Northbound API, and we would set up the flows. And you could kind of have a LISP traffic going from a LISP mob node to an OVS. But that has a little bit more steps involved, so it wasn't appropriate for the talk. However, we're going to have better integration there as well to run everything smoothly. So now I'm going to pass to Sharon from ConteXtream to talk about the NFV side of things. And then maybe at the end we'll do. Okay. Oops.
Hello?
Yes, LISP has Wireshark dissectors. Sorry?
Can you see the encapsulated packet?
You see everything. So there is again, Lori has done the Wireshark dissector for LISP. You can see everything, including the path policies, service chaining policies, the weights and prior, everything is there. I'll leave that for Sharon to respond to. Thank you.
OK, so I have just a few minutes to illustrate why we chose LISP in ConteXtream. We're an SDN company, so why to us LISP was not another routing protocol, and why we think it's critical as much as OpenFlow in creating scalable and resilient SDN solutions. So the domain we operate in is NFV, and as you can see on the left side versus the right side, here's the transition which is happening in the industry. So basically, carriers are moving away from a model where they put functions on routers to putting functions on servers. The problems with the right side or left side of the picture is that whenever I add functions to routers, then I have to synchronize roadmaps of multiple providers, vendors. It takes years to do that. When I turn functions on, then I have to split the aggregation to accommodate for the fact that the capacity of the node is going down. And I have to deal with lots of boxes. Just in the case of mobile core, I have to deal with DPI, packet PDN gateways, IMS cores, session border controllers, load balancers in every hop, and additional functions like transcoders, firewalls, and so forth. In the right side, we are moving to a model which is a lot more data center-like for network functions and decoupled from routing. In order to do that, we have to find a new method to do virtual networking. So if on the far side, the traditional virtual networking had to do with VLANs, VPLS, MPLS, was very tied to the routing interfaces, we have to move away from that to something a lot more dynamic. And this is what LISP allows us to do. So we will move from a very structured but very static virtualization structure to a very dynamic one, which is based on LISP mapping and overlays and underlay infrastructure. So this allows us to move into existing carrier environments because we're not going to put an OpenFlow controller because we're talking about, like today for us, just in one carrier, tens of billions of flows per day. So we're not going to load any one controller with that. And we're talking about deployments over the entire US. So there's no one controller position which is right for that. Therefore, we don't put anything in the center. We just put the underlay network. And the underlay network has the quality of providing two things using the LISP architecture. One is transport. If I take a packet, put a header on it, it will show up where it needs to go in the right function. And the second one, if I take a query and I put the right header, I will get an answer of what I need to know. So when I'm doing overlay, I need to know what's beyond the overlay. In the other side of the underlay, I have to have that mapping capability. And this is basically the qualities of east-west scaling we put into OpenDaylight together with Cisco and LISP, and this is how we use it. Here is the basic characteristics of why we chose Lisp and why we went to Joel from ITF with the permission to make Lisp an SDN protocol, and what else is needed in order to be able to do that well. Let's take a look at a node. When we build an SDN for NFV node, what do? We start off with some kind of physical aggregation, a switch. It can be an OVS if it's in the host. It can be a real switch if it's aggregating in network as a Lisp edge device, Lisp SDN edge device. This device aggregates what we call outer lay things, which is access, subscribers, mobile networks, backhaul networks, and functions, which is servers. So it can be either or both. It doesn't really matter. And we put the OpenDaylight controller right next to that physical switch. So we don't worry about consistency between the controller and the switch. The OpenDaylight controller, has the same shared fate as the switch. And that allows us to build a consistent overlay. In the OpenDaylight controller, we have flow handlers for the various types of traffic. So I think Vina demonstrated IP and IP chaining. We have, in addition, SIP-specific flow handlers. We have EPC flow handlers, and this can be added on by anyone using the package. In addition, we have, of course, the OpenDaylight mapping system, in which when a packet in comes into the flow handler, we can do EAD to RLOC mapping and ask questions. Where is the best destination for it? Which RLOC is the best destination? We can also put KPIs. There was a question on that. How do I know what the load? I can basically put all that information into the mapping system. And then we make the decision. The methodology is map and encap. So I did the mapping for the first packet. I encap for the whole flow. And then I put it on the overlay. Here's the basic layout, typical layout. Used by ConteXtream today for map and encap pre-standard, and moving towards OpenDaylight deployment once it's a little bit more hardened. It's basically talking about in-network aggregation, so it combines overlays and OpenFlow to build in-network overlay aggregations. It aggregates access, the internet, and functions. And it allows management and orchestration to plug in information. That's the structure of how we talk to the north using schemas of the mapping system. So the orchestration will instantiate functions, and it will put in the mapping system not only what is that instantiate the VM, but what is this VM? Is it a firewall? Is it a packet gateway? Is it a parental control? Is it a transcoder? And so on.
How are you able to make your control and host switch share the fate? How do you enable fate sharing between the transport element and the computer? Is it, for instance,
the fate sharing is because these X boxes really represent a node which has an OpenDaylight controller for that aggregation only. OpenDaylight controller here does not control anything else. So as long as you can reach the controller, you have reached the RLOC, so you know it's alive. There is no ambiguity whether the controller can reach a node, but the other node cannot reach that node, or vice versa. We reduce those consistency questions significantly using this structure. So it's not a fully loose structure of SDN, controller in the cloud does everything, but it's a lot more flexible than VPNs and MPLS, which don't allow anything to move because they're tied into routing interfaces. So it's a good middle ground for that. Yeah. And there is a whole Dino set of presentations on how you do that, using RTR for replications. So. OK, let me just illustrate some chaining, balancing decisions for functions done this way. So I'm not going to go into details, but traffic comes in to the aggregation of the outer lay. There is a map and uncap decision made, and therefore you show up on the other end because it's the best resource, in this case, session border controller. It is the least loaded. It is the best global decision, or locally made over there, right there in POP A, but globally aware. And other scenarios where you end up in one place, start in one place, and end up in another. So this is how we use mapping and cap today, and this is what we started to contribute into OpenDaylight together with LISP and Vina and Fabio and team. Is just a net list of components that you can, some are there and some anyone can just build on and extend. The OpenFlow switch is any OpenFlow switch. We use it mostly for 3-tuple. We don't load it with 5-tuple because in carrier environments, we're talking about millions of 5-tuples. But we use it to service selection, to do service selection to the right flow handlers. And to do basic SDN services like virtual layer 2, virtual layer 3, sort of the simpler services. In the forwarding, we have software forwarding, which is part of the service selection, in which we do the 5-tuple scale out of subscriber flows. For example, all the iPhones in one large carrier in North America. And then also application-specific flow forwarding when you need deep NAT or high touch, which is specific. On the control side, we have the OpenDaylight SAL, which has the packet in, which selects between the right flow handlers, if it's basic IP service, or if it's more specific, EPC or SIP or other. And we have the mapping system. Okay, again, you have a basic mapping system for free in OpenDaylight. You can extend that by, that's what's nice about LISP map and cap, is that it allows you for flexibility in what mapping, what's the mapping function that you're going to use. It doesn't force you to use a BGP or broadcast, which is very hard to maintain consistency. It lets you choose something that scales to your environment. That's it.